We are going to talk about system design fundamentals. So it is to build a scalable real world systems. We'll go over the basics of system design, what needs to be considered when plan for a system design, and what are the core principles that we need to keep in mind, and how we need to do the trade-offs between the different tools or applications or databases, how we need to do the trade-off. And finally, at the end, we can look at the one case study as a real-time example application like Amazon e-commerce platform, online marketplace platform. We can look at it at the end so that whatever we covered in the topics, we can look at then the case study. So at the end, in the 5 minutes, we can uh, interactively discuss about the questions and answers. Yeah, let me go over the agenda quickly, the session. So what will be covered here is what is system design, core principles and scalability patterns and databases and case study, as I just mentioned, agenda. And yeah, we'll see what is system design in a nutshell. Yeah. So system design is all about it's architecting a system with the components and data flows to satisfy the business requirements at scale. So it is all about trade-offs that we choose while building a system. So there is no one perfect solution for a system. So it's all about based on the requirements and based on the some numbers, the amount of users that are going to use this system, and if the users really need very low latency response, we choose some of the tools. And if it is, if the system needs very high throughput, we trade off some of the other things. And if the system needs a strong consistency, we choose a particular database. If we need a flexible schema, we choose a flexible uh, schema database like NoSQL database. So it's all about trade-offs. And a good system design, in a way, it will scale with the users. Even if it starts with 1,000 users, if it ended up having a 1 million users, the system should support. I mean, if it is designed for 1 million users, so that we need to design accordingly. So the key things that we need to consider in every design is, first we need to clarify the requirements and constraints. We should not go for drawing the sketches in the first moment at any design. So first we need to get requirements clearly and constraints, and also the transactions per second, requests per second, whatever, and the systems are involved. What is the inter-service communication and all. So first we need to overall gather some good amount of requirements on a high level and constraints. Then we can make the choices accurately. So instead of directly drawing components and like that. So this is all about engineering mindset we need to have while designing a system. So otherwise, what will happen is, like, if the system design is poor, later if the users are increased, it suddenly the system is not scalable, and there is a lot of rework and cost for the business. So it will eventually impact to the business. So we need to keep all in mind, and we need to have our system scalable. So having said this, we'll go for in a structured way. So in a how we can structurally gather the requirements in a uh, for a system. So let me go to the next slide quickly. Let's talk about. So in a system design, we need to consider functional requirements and non-functional requirements. So as you might already aware, the functional requirements is like actual functionality that we provide for a system. For example, sign up is a functional requirement, login, and making an order, right? So these are the functional, clear requirements that user experiences on our system. So most of the people think about when talking about system design, they will just go ahead and implement this functionality and get it done. But uh, probably juniors may tend to work on functional requirements more closely. So in general, we give functional work to the juniors, and some senior members more focus on non-functional. So it's overall, we need to design a good scalable system. So when defining a system, non-functional requirements are very important because functional requirements just satisfy the users at a minimal scale. But if we design a system keeping the thing that non-functional, right? So we should not always think about the happy parts in production, which we can expect anything, database failure, network partitions. And so we need to design a system for partial failure and to have a fault tolerant. And some of the non-functional and specifically defined terms we have, like the system should have a proper availability and latency and scalability and durability and security. So we will talk about each of them clearly in the next slides. But overall, whenever we asked for a system design, we need to come up with the functional requirements and non-functional requirements. So if we satisfy both of them, the system is it will work in a fault tolerant way and it is scalable. So that is the high level idea. We'll go over one by one. So so one attribute, the important attribute that we placed right next to the system design is scalability. So this is the very every system should have this property for a system, because otherwise, if the system does not scale, the business will does not grow and does not support the customers, and customers may feel that this system is not supporting well, and user eventually we face a user experience issues. So that should not happen. So there are two things to solve this scalability thing. So structured way, we can have horizontal scaling and vertical scaling. So primarily when start working on a startup project, we go with the vertical scaling. So initially we don't need to do horizontal scaling, load balancer and everything. We should not do over engineering initially. We should start with vertical scaling initially just to have economically good. So once the system is stable and if we have a good amount of users and all, we eventually have scale this to horizontal scaling so that we can have horizontal scaling. So the primary difference is like vertical scaling is nothing but we are just improving the existing machine itself. We are increasing this processing power, RAM, and disk space and all. So we should, when the users are increased, we should definitely go for horizontal scaling. Otherwise, vertical scaling will be a single point of failure, and we should avoid it. So in the modern tools and cloud services, everything is horizontal scaling. I mean, we can add as many missions as we want dynamically. If the users are increased on a particular day or a particular hour, the new instances will be added and scale out and scale in dynamically based on the traffic. So yeah, that is the primary difference between vertical scaling and horizontal scaling. So horizontal scaling, the one overhead is like we need to have a load balancers. When multiple instances are serving the user request, we need to have a load balancer which will make sure to send traffic accordingly. So there are several algorithms for it. There is a round robin algorithm to evenly distribute, and there is a least connections algorithm. It will send the traffic to the server which has the least connections. So based on the uh, requirement for that application, we can choose that one. Just to aware of that, there are several algorithms to choose and distribute the traffic. So horizontal scaling is the preferred one to have our system really scale, uh, not linearly. Yeah, we'll go with another property. Okay. So coming to the another properties, like our system is scalable, that is fine, and it's serving the users. What about availability and reliability? So there is a primary distinction between these. Availability is our system is available. So any system needs some downtime. So we should not say our system is 100% available, but we need to take some trade-offs. Like it comes with a cost for a particular business. So if the trading application kind of thing, we should need 99.999. So If you look at an example, we can calculate availability like it is an uptime divided by uptime plus downtime. So as an example, if you take 99%, here my system is 99% available. It means it is down for 3.65 days per year. So it had two nines availability. Maybe some of the systems, it may be okay to have 99%. With respect to that, they can design the system. If the application doesn't tolerate this downtime, we should opt for this one, maybe five nines. So it is a trade-off that we need to choose based on the application whether we should support two nines, three nines, or six nines. So it is very high available system, 99.999 finite. So this is the availability kind of thing. So it can serve most of the time 24 by 7 for the user with the least downtime. This is about availability. So whereas reliability is like we should give a proper response to the user. I mean, even though system is available, but we are giving a wrong data, that's not reliable. So our system should have a correctness and give proper result. So then only we have a trust on our system. It's a reliable system. So these should go hand in hand. System is available and it should also be reliable. So availability without reliability doesn't work. So we need to think about reliability. And sometimes it's okay to fail the request and give a graceful message to the user that it's not working, or whenever something bad happened on the back end. So we make sure to have a proper information to the end user. So this is the one consideration we need to keep in mind when designing a system. Let's go to the another some properties like, so in a distributed system, there is a cap theorem. It is about consistency, availability, and partition tolerance. So what happens is like it is actually tested by a person, some of the engineers, like in a distributed systems having these three things, having consistency, availability. Uh, we cannot have a system with consistency, availability at a time in a distributed system. I mean, like for example, we'll quickly talk about what is consistency, availability, then we'll. So consistency is nothing but every request receives a recent write. I mean, if the database is updated with the value x equal to 5, if another person reading the data from a different node, he should also receive the value of 5, not the 4. I mean, if it is an increment operation. So that's how the consistency system. And availability means like irrespective of, so for every request we will get a non-response error. So it is doing some compromise, like even some of the node it is okay to return a 4, bit of stale value availability, but it's not it is available and probably return a stale data. That is about availability. So in the consistency, what happened is if the data is inconsistent, it may give a failure response instead of returning a incorrect value. It will return an error. That is the major difference between consistency and availability. And partition tolerance is nothing but in a distributed environment, uh, network can fail anytime, and any part of the system. If you have 100 microservices, it is fairly possible that some of the system is down. You need to handle accordingly. So in a distributed system, having partition tolerance is possible. We need to design our system. I mean, if it is a banking application, we definitely need a consistency over availability. So for a consistency and partition tolerance, we need to design a CP systems, consistency and partition tolerance. So come to the consistency, we need to choose the database accordingly, like PostgreSQL, MySQL are very good at consistency because these are very good and legacy relational database systems. I mean, latest is also fine, Aurora and kind of thing. But for a consistency, we definitely choose a relational database systems, and we will have a data very consistent there. And coming to the availability systems, availability and partition tolerance, like our social media applications, like what happens is if there are 1,000 likes for a particular post, even if we show 999, that is fine. If you go with that kind of thing, it's not a very critical application. we go with availability. Like many of the social media applications, bloggers, and read-only systems, we prefer availability over consistency. Consistency doesn't uh, play a key role there. So based on the application, we need to choose whether we need CP application or AP application. Sometimes we can support both. I mean, it is a single node application. So nowadays, most of the applications are microservice architecture. So, there could be monolith applications also. It has its own advantages, like it can provide consistency, availability at the same moment in an application. So it's a basically single node application. Everything is present in the single application, single database, single application server. So we can achieve those in the single node. So these are the trade-offs we need to think about while doing the system design. And once we have CP or AP is defined, so we need to think about how will be the user experience. For some applications, like trading applications, we the latency is very critical. We need to receive response very quickly. We should not wait. We should not have the user to wait for the response. And some of the application need very throughput. I mean, some a couple of events or work needed to be done in a given time. So overall, the performance of an application is defined through latency and throughput. The primary difference here is latency is nothing but a time to complete process a particular request. It is the latency, and throughput is number of tasks, number of operations complete in a given time. So high performance system is nothing but a low latency and high throughput. So if the application needs low latency, high throughput, if the application is low latency and high throughput, it is a high performant application. So there are several techniques to achieve this low latency and high throughput. We'll talk about that in the next slide. So the only thing to remember is these are the two properties that define the performance of our application. Based on the application, we need to build the system accordingly. And coming to the load balancer thing. So So this load balancer in distributed applications, we need to have a load balancer to distribute the top traffic across the servers based on the algorithms. Like I mentioned earlier, there could be a round robin algorithm, least connections algorithm. Based on that, traffic will be distributed to the different servers. So that if the traffic is increased at a moment, I mean, on a prime day, on a particular day, on a particular hour, the users are 10 times more to use that application. At that time, our system should scale at the moment. So based on the traffic, load balancer knows that, but with respect to the user, it will check the health of these servers. It has some capability to have some monitoring on these services. I mean, health of the server, if there any server down or up. Based on that, it will span multiple servers instances to serve the traffic accordingly. And after the traffic comes down, it will scale in the services. I mean, load balancer is, if you take an example, Amazon provides a elastic load balancer. So based on that configuration template, it will scale out the services and scale in the services automatically. So there is no manual intervention needed. That's very ideal because when the traffic increases, we should not have a manual intervention that let the system scale and serve it and scale out. So that's the idea about having the load balancer. And also talk about API gateway. So basically, after load balancer, we would expect a API gateway also to perform any operations, specific operations like TLS termination. It may be routing and any common logic, any rate limiting logic. We can all have after load balancer as an API gateway, and then we can have the services. So coming to the one important thing is rate limiting. Like any system we design, we should have it will have some limits on the CPU resources and the capacity of the servers and all. If the clients misuse the our application in a bad way, if they are sending thousands or millions of requests for a minute or our systems will impact the actual users. So online marketplaces, it will be a real challenge. We need to have some limits on the client usage. Then only we can have the fair usage of the resources and so that a real user will not be impacted. So nowadays, anyone can make our system down if we don't have a proper rate limiting feature. So this is one of the important thing we need to consider. So for this also we have several algorithms to achieve this. So say for example, if you look at the diagram, there are many requests comes in, but we serve our service in a controlled way using respective algorithms like token bucket. If you take, it will allow these many requests to serve. And there are some minor differences between these two based on the application we can take it. And there is a fixed window. So it will take per minute only these many requests it will serve. And next minute these many requests. So it is somehow, it is one of the technique to have our to fairly usage our resources and to avoid any abuse from the different clients. So this is the one important feature we need to add to our systems with respect to the application. Coming to another, so in a system design, database thing is also very important design aspect. As I mentioned, like based on application, we need to choose. Hey, I'm building a one application. Let's have MySQL or PostgreSQL. That's it. That doesn't work because nowadays the application needs a different things. There is no good and bad about SQL and NoSQL based on the trade-off and application use we need to use. So we'll talk about difference quickly, a high level. Like when it comes to the SQL, it has its certain capacities. Like it's good at a strong schema and ACID transaction. So it will maintain atomicity, consistency, isolation, and durability of the data, and it will provide pretty much good complex queries for all SQL databases. So we can join the databases and get our required data. So the well-known relational database are Postgres, MySQL, and Aurora. So Aurora is Amazon's provided MySQL database. So when you care about the data integrity of the data, and we need to query the data efficiently and store the data in a structured way, in a normalized way, go with the SQL database. And NoSQL is we have some of the, for example, SQL is for if you have a payments and users kind of thing, you definitely choose SQL database. For example, you have a flexible data. For example, there is a order, and if you are purchasing products on the online, there is an order, and some of the data we can observe. Those are flexible. I mean, flexible schema. We can add as many properties as we want. So the schema is flexible. Basically, you don't need to write a SQL schemas to apply the schema into the database and all. So NoSQL will evolve with our model. It can be a Java model or gRPC, whatever, irrespective of the language. If the model, if you add some more properties, it will evolve the schema and it will store the document accordingly in the NoSQL database. The schema is very flexible. Some of the data may have 10 properties. The same data, order data, can have 100 properties based on the user choosing the list of items, as an example. So NoSQL will have a flexible schema, like it can scale horizontally. So it's a key value store. It has its own advantages. Based on our use case, we need to choose NoSQL accordingly. So there are some other databases also, like Elasticsearch and Graph databases. Those are for different use cases. Like uh, Elasticsearch is used for like indexing our search results to access the data frequently. This kind of databases will be useful. And coming to the one more point, like when we have a database, we should not have a single point of failure. Like uh, we should have a primary database and replica databases. We should not rely on the single database for read and write. Probably we could have a primary database for writing the data, and we have another database is replicating the same data asynchronously as the replicas R1, R2, R3. So for all the read operations, these replicas will be useful so that we cannot overwhelm the primary database. It is for writes. So this way we can, if the system is okay to have eventual consistent data, we can read the data from here for all eventual consistent data. But if we need any critical data that needs very, very consistent data, we can query primary DB and get that information. So it's all about the trade-off, and based on the use case, we will play accordingly so that we can efficiently serve the users and uh, yeah, based on the logic. And sometimes sharding is also needed. It is we need to choose accordingly. So I mean, sometimes this is fine. Replication having primary data and the replicas will serve most of the systems. Sometimes if you have a million, 3 million records are there. So for all the users serving the same database may not be a good idea. Sometimes we overload the system. Single system we are overloading for these users. If we are logically separate the data, I mean, this is all about uh, scaling the database in a sharding manner. I mean, based on the user region, maybe by the location, all Indian users use this database based on the location, based on the country. It is as an example I'm saying as an attribute. Hey, all users belong to these properties going to this database. Users belong to this property going to this data. So that we'll have a sharding. So that we'll have a multiple databases. So when the request comes in, I will go to the shard A or B or C according to the user. So this way we can reduce the load on the database. So this is for special use cases. We use sharding. That is a high level database design, and we need to trade off between SQL and NoSQL. We'll go quickly. So we also talked about the performance of application earlier, latency and throughput. So we cannot achieve directly. So those are the properties we need to achieve for our system. To achieve that, we need to have some strategies. So definitely every application needs a caching mechanism. There are several caching techniques are there. Like as we know, caching is to reduce the load on the real primary source of truth database. So we should not call the database for everything. So if there is a frequently accessed data, like in an online marketplace, the products are frequently accessed by every user. We need to show the product catalog. Probably we can cache those kind of metadata kind of thing so that we can serve from cache. Whenever that particular data is updated, we need to properly invalidate that cache. So we need to, so when we have cache, definitely it will improve the performance. It will first check with the cache. If it is a read through cache, for example, we'll talk about specifically read through cache. App will check for cache for a given key. If it is present, it will return. If it doesn't present, it will make a call to DB and get the information and put it in the cache and serve it. Next time when the request comes in, it will serve from cache. It is the read through cache. So there is a write through cache also there. First we'll write to cache and also to the DB and serve the request. So for the next user, if he try to read it, he will get it from cache. So there are read through, write through cache techniques are there. So the tricky thing is when are we going to invalidate the cache data? That is the important thing we need to consider. Otherwise, if we serve the unreliable data, so our site will become unreliable. So to have a reliability, we need to make sure to invalidate the cache whenever the real data, associated data is updated. So that we can the application serve the data accurately and efficiently with the caches. So probably we could have Redis for uh, Redis cache and memcache. To have only simple key value store with the high performance, we go with memcache. If you have a specific features to support different data structures like list set and so on, we use Redis. So there is a CloudFront also there. It is a content delivery network used by the mostly like if you want to store a static content across the world. So if there is a large amount of data like movies or web series or some kind of files, we can put it all the static content on the CloudFront content delivery network servers. Like there are bunch of servers worldwide. There are specific to serve the static content. So when the request comes in, it will go to the specific server nearby location and get the data. So that we don't need to ask the primary stores. So that is one of the technique to serve the content for the user very quickly. So these are all the high level details about the caching technique to improve the performance of the application. So another thing for an application is, so uh, for an user experience point of view, we see that we are interacting with the system, we are getting the response quickly. So when we make an order, we get the response, your response is successful. But behind the scenes, there are a lot of operations to perform by the application, like it may update analytics information that I've purchased this product, and it needs to send an email, and it needs to update another table, and so on. There are many things. As an example, email we can take. So these need not be done synchronously. If these are done synchronously, client will wait for a few seconds, maybe 1 or 2 seconds is also very big delay. We should avoid that. We should give the response very quickly that you have ordered, you have completed order successfully. So behind the scene, we need to perform some more operations that we need to design for asynchronous communication. So for example, in the order is placed, we can publish an event, order created event, and it whichever the service need that particular event, like email analytics, will use that event and process asynchronously. So from user experience standpoint, he ordered it and he will get a response quickly. So these are the things we need to keep in mind, like which operations we can make asynchronously and which operations are synchronous, so that we can have a efficient user experience, and we can handle the load very in an efficient way. So for example, if you take the Kafka, it can handle millions of operations per second. So for high performant applications, real-time data streaming, we could use this Kafka. So if our application is doesn't care about millions of operations per second, that kind of performance, if we don't need, we could use RabbitMQ or AWS SQS, those kind of things. So this is how we need to make a trade-off based on the constraints and the requirements of our application. We should avoid over engineering our application. So based on the user's constraints, we need to take a decision, and also we need to think about in the long run what is the predictable load for our system. So we can build the system only for a predictable load. So we should aware that, hey, my system will support 1 million users fairly. So if we have that confidence, so we can build the system in that lines, and it will definitely support it. So that's how it should be when we design a system, uh, to avoid any surprises in the latter. So in that, the synchronous communication plays a critical role for the high volume data processing. So yeah, so it is more related. So when we talk about the previous thing and this one, so as we talked about a little bit earlier as well, so synchronous communication is like user waits for the response for at that moment, request made. So this is a synchronous communication, and if user doesn't wait, that is a asynchronous communication. So behind the scenes, we publish to a queue or Kafka cluster or whatever as a central hub. We will push our event, and the consumers will read the data. Some consumers will pull the data and get it and process the event. So there are different models. There are push model, push based, and pull based models are. Irrespective of those models, it's all about asynchronous communication. I will put the event and consumer will process it. So this is the asynchronous communication we use. So in system design, we need to define which operations go for synchronous and asynchronous. So for synchronous, as I mentioned, if you do an order, you will get a quick response, and behind the scene, we send an email with the asynchronous communication. Like we'll put an email order created event, and the consumer will process it and sends an email. So that's how. Coming to the another trade-off that we need to think about is REST versus RPC. Like there are many, I mean, these are well-known APIs that we need to have. So in the distributed microservices communication, so the services needs to communicate together because all services are there to serve a customer as a common goal. So this all becomes a one system. We are just building it as a microservices just for the sake of flexibility to have to scale independently, and so it has its own challenges. So at any point, so we need particular contract for a any service. Hey, this is a service. For example, payment service. I'm responsible for all the payment things, payments, refund, and all. We need to define the contract there. So coming to the we need to define. So if it is a publicly exposed API, we should definitely go with the REST. So it's a representational state transfer and it's a well-known HTTP based thing. It's a resource oriented and it will use HTTP methods like get, post, put. So when we are designing a REST controller, we need to think about if it is to read the data, we need to use a proper HTTP method get. If we are creating a new resource on the server, we need to use a post method. If you are updating a resource, we need to use a put method. And if you want to update the status of the resource, we need to use the delete API kind of thing. In backend, we will just update the status to active or closed like that. So if we maintain this structure for the REST API, any developer can easily understand the requirement, the controller and everything in the REST API, and he can enhance it. So that is the important thing to use proper HTTP methods, and we need to also think about Get API. So Get is also idempotent, and yeah, the only thing is we need to more aware of the HTTP methods, which HTTP method for which operation. So on a high level, it is a CRUD operation, as we know: create, retrieve, update, delete. So these are the fundamental operations that we perform on any entity, any object in the system, whether it's an employee object, order, or it will undergo these fundamental things. Accordingly, we will design the REST API. And so another thing is, say for example, these are the public exposed API. I need to have a communication between the services. Those are the internal services. I have 20 microservices internally on my server. Those needs to be communicated. So these services are not exposed to external user. External user will get the request from the API gateway, and we internally serve that process the request accordingly. To have inter-services communication efficiently, we don't need to build the REST API contract. That also works, but nowadays gRPC also preferring, so it's very efficient. So it will execute another operation on another mission. So it's a remote procedure call. Uh, Famously, we are using gRPC. Google. It is basically it's implemented with a Google remote procedure call inside the mesh. So for the inter-services communication, use the RPC. For external APIs, use the REST API. So that's the thing we need to remember. So in the slide I mentioned, so primary differences, you can have a look at it. Both will serve on the HTTP 1 and 2. The REST API is human readable. That's how it's less efficient because it's not friendly for the machines. So, but RPC is a binary compact. It's very good for the machines to understand and process quickly. And there is a protobuf is there. We can define a proto like our REST API. We define a contract, right? For a proto, we define a contract there. Hey, this is the message. This is the my request. This is the response. If you define that one, we can pretty much create the stubs in around many languages. I think 10 plus languages we can generate the client stuff, client and servers we can generate. I mean, as a boilerplate code, we can generate quickly. So there's the advantage we have here. We'll go to the next topic to cover all quickly. So coming to as we are discussing, yeah, some of the topics are definitely overlapping here and there, but specifically we can look at this one also, as we thought about monolith and microservice architecture. So when we start with an application, definitely we go with the monolith architecture. And once we are good at understanding the things, modules, definitely in the monolith architecture also, we should have a proper packages for a particular model. We should not put the models in a core layer. So we should divide our models, our service layer, our database interaction fairly in a packaging structure, at least in a monolith. Eventually, if time comes, we need to have this application really scalable, because scaling the monolith is possible with some extent using a vertical scaling. We can increase the power per emission and everything. If the team is increased and working on a monolith application, it is difficult to scale the application, and engineers will overlap on the things, and there is a lot of effort we need to put to manage a monolith application. For a simple change in auth module, we need to deploy the application. If you need to make a change in payments, we need to deploy entire application. That's the thing we need to face in the monolith architecture. So once we have the monolith architecture application in a structured way, if we implement in a separation of concerns, we can easily split into microservices so that eventually these will become auth microservice responsible for only auth, and it will respective DB, order service and payment service and users. So as we are gaining some advantages with the microservices, there is challenges also. So microservices easily scalable. We can scale these payments service horizontally, like using load balancer, whichever services needs more. But inter-service communication is a challenge. We need to define proper contracts, and we need to consider network failures. And if there is a failure happen, we need to recover easily. I mean, we need to build the system for the partial failure in the first place itself. We should not think about the happy parts. We should think about every API call is a partial failure. Accordingly, we can communicate the user. Sometimes the system will automatically recovered eventually using our jobs and asynchronous communication, systems will recover. We need to have that kind of mechanism. So this way, what will happen is sometimes if the one of the service is down, it's okay to serve the request, and eventually that particular consumer is maybe down for a moment. It will process after a few seconds, and the system state will get settled in some seconds. It will be usually in milliseconds to seconds. System will be stabilized. And in a microservice architecture, important things to call out to remember, like uh, so we will have a technology freedom in the microservices. Hey, there is emerging technology. I need to build this service in the Go language using Go, gRPC, like that. We can build it without impacting anything. We can just have our own stub in the client. I mean, if you build, we can have a Java service, Python service, Go service, like that. If you have a gRPC. Like that, we have a technology freedom, and small teams will just focus on authentication team, orders team, payments team. So you have a clear responsibility, and teams can clearly own the things, and they will eventually solve any real issues because the ownership is clear and independently deployable. There is no interference between the teams. They can just if there is any dependency, we need to communicate. Otherwise, we can develop and deploy independently. That's the advantage we have, and also challenges. The architecture. So one of the critical and important things for the system design is security. So it is a business agnostic. For any system, we need to have these two things as a common thing. I mean, the level of the system, if it is very any system, we need authentication authorization. Some of the systems, uh, it is the level of the system. It is the banking application, for example, or definitely probably any other systems also. But the level will, the scale will, we need to choose. So any system that is used by uh, it will be used by users or a service. These are the two things we need to have. So that we need to have our system to authenticate a user. So authentication is nothing but to verify the identity of the user or a service which are going to communicate. Once the authentication is fine, hey, I have the known user, so that I can allow to process some request. So what happens is authentication is not sufficient. Hey, I have the authentication, I can do anything. No, so authentication authorization plays a role in this system. You are given specific roles. The roles can be a different thing. It can be a role-based access, attribute-based access. So role means it's a manager role, admin role, those kind of thing. Attribute means based on location, some of the attribute kind of thing as on a high level. So based on the authorization only, you can perform on the limited operations. So the preferred way is we need to follow the least privilege principle. We should not give all privileges to every user. Based on the user, we need to give the only least privilege, only needed privileges we need to give. So that way we'll have better control on the system and should not expect any abnormal behavior from the users. So these two are the things. Authentication, authorization go hand in hand. And so in the systems serving for millions of users or thousands of users, anything. So if the volume is very high, we definitely see a, different kind of issues like unexpectedly if some of the system is down or any issues from the member, anything can happen in a distributed system. So we need to have a proper logging for the errors or warnings. Uh, Maybe it is okay to don't log the fine messages, but if there is any warnings or error, we should have the logging and proper alerting mechanism so that developers can fix it accordingly. So this is the monitoring. We build the system. If we don't have the monitoring, we don't know whether it is working fine or not. We should have better control on our system. So by looking at the tracing and metrics and all the dashboards, we can know that our system is working fine. Otherwise, there is no way to know whether our system is functioning properly or not. So we should not query the DB and check, right? So we should have a proper dashboards and loggings uh, to monitor our system. So this is the important for the operations. So these are the granular things for the specific metrics we need to have a proper metrics. The tracing mechanism, it's important thing. Once a request is made, it will go through internally a couple of services. So we need to have some kind of techniques we need to use like open telemetry or and trace ID. So once the request is initiated, we create a unique UUID. So it will go through all the services and will have a proper tracing for the request so that we can easily find out the bugs in a particular microservice kind of thing. So end to end of the request cycle will have the trace. So this is the one in trace ID. For every request, we need to have a trace ID, and we can use different tools like Logly and Splunk to track that request. So alerting, as I mentioned, we need to have a proper alerts for the severe errors, so that these are the real issues that we need to solve uh, quickly to reduce the impact on the user. So yeah, we are getting the end quickly, and we'll. So any system design, we need to come up with the questions. Not we should not go with the starting diagrams and all. First, we need to clarify the requirements and scope. Ask as many questions as possible. Once the constraint, scope, and everything is defined, then only first two things. I mean, estimate also queries per second and everything. Then we can slowly, as a low-level design, we come up with the API design. How the API design should look like. What data bases we need to choose. Sometimes we need to choose MySQL, NoSQL. For some of the data, we need to use relational. Some of the data we need NoSQL. And then slowly we need to come up with the architecture diagram. Then we need to retain the components and cache mechanism, Redis or Memcache. So, and for the scalability standpoint, we definitely go with the horizontal scaling by design so that we can fairly uh, serve the traffic. If the traffic is increased for the prime day or particular hour, we should plan for that. So we should start with the simple and iterate over it. Coming to the case study, we can quickly apply our knowledge so far we gained on a high level. So as we know, every topic as its very detailed discussion is needed for anything what we covered. If it takes low latency, high throughput, or SQL versus NoSQL, or caching mechanism, or availability, everything has needs a deep understanding. So we came to know high level idea about each and everything in a very high level. So having said that, we can quickly go over this application, how it will look, how we can apply our knowledge to this application. live. So the case study is the very known application we have taken, like Design, Amazon, Scale e-commerce platform. So our problem, I will just talk about. So Design, a globally distributed e-commerce platform that lets users browse, search, purchase, and track products with high reliability during normal and flash sale traffic. Browse and search catalog. Those they are the functional cart, checkout and payments, order placement, tracking, returns, product recommendations. So the requirements are clear here. Like as a user requirement standpoint, so user should able to browse and search catalog and cart, checkout, payments, and product recommendations and all. So as I mentioned, we need to ask the questions like how many users does it should support eventually. I mean, when we are building the application, maybe it will be 10,000 user, 1,000 users initially. Slowly, our application should support 300 million users also, 12 million products in catalog, 100K peak orders, like that. So availability standpoint, we are okay with the four nines. Having said this, so we need to make the trade-offs. I will show the trade-offs how we can make it. So this is the high-level architecture we have. So so definitely the clients for this application are like desktop web, and mobile apps. It can be iOS, Android, and sometimes can be admin portal, partner APIs, then a third-party integration. So there are several clients for applications that we need to draw here. And as we discussed, there could be some edge locations we need. Amazon services like uh, frequently used data, media files is there, some videos are there. We can put those in the content delivery network to serve globally. As it is a global application, it can reach out to a nearby location and serve it. So we need to think about those and load balancer, and we need to have a proper API gateway layer there for the contract, and there is a backend for front-end layer like GraphQL layer. For some of the modules, we may need different layers of application, and also a rate limiter for the application, right? So these are the high-level things we see, and behind the scenes, it is served by the microservices. We can have a gRPC mesh for that. So we could have a product and its own DB and search feature, and the catalog and its own DB, like this. These are the microservices responsible for each one. And sometimes we need asynchronous communication, like we need some workers like to asynchronously process the events. Like there is a payment successfully, payment initiate, payment is completed, probably payment is completed, that particular event is consumed by the email worker and sends an event to the user. So there is sometimes there is a new inventory is added. There should be inventory created event is added, and search indexer could consume it, and it will update that index so that this uh, latest product will be shown on live. So these are the things. And for asynchronous communication, we should have some hub. It could be RabbitMQ or Kafka. So here the volume is high. We need very low latency experience for the user. Like this application may serve okay for all days, but on a prime day and a particular hour, to support that particular hour, we are having this many constraints and tools we are using. Kafka, it is good at processing millions of operations per second. So we definitely need to take some trade-offs to have, that is very critical for the business to serve in a flash sale. So then only this application is very available and reliable, and low latency experience for the user. So coming to the databases things, so when building an Amazon, I'm using PostgreSQL, NoSQL. That is not sufficient. So as for this kind of application for these users and functionality, we definitely need caches also, Redis cache, Memcache, wherever needed wherever strong consistency is needed for the integrity, for kind of inventory, payment, for critical things, we go with the Postgres. For any orders kind of thing, catalog, for a flexible schema, we'll use DynamoDB. for the document database for analytics. So analytics also an important whatever the data comes in, we need a regular data feedback for the analysts and the products to analyze to iterate over the product. Based on the analysis, they cannot imagine the things. They will look at the data, they will come to some conclusion. Hey, this product is purchasing by the customer very frequently, or some kind of, as an example, what is happening over a period of time in 2 months, what happened, what are the purchases happened in this area. So we can product will focus on that particular area and enhance it so that they can get the revenue quickly. I mean, time to time the application needs to be evolved so that it can serve up to the competitors like Flipkart and other things. So that is the tricky thing. So all could be possible only with the analytics, the data, so that we'll have a dashboards accordingly, and based on that product, make a decision and iterate over the product. So iterating the product is a continuous thing. So in a software application, there is no final product. It's a continuous development and continuous iteration based on the revenue and user experience. So for that, we use analytics tools and observability, Prometheus, Grafana. So there are here mixed something technical tools, open limits for the developers to track the request, and some of the dashboards we need to build for the products also. So it's based on the product requirements we build and show it uh, as an ad. So coming to the hope it is okay. We are getting 2 minutes, but I will wrap it up in 5 minutes. Okay. So coming to the and so whatever we discussed, we can look at in a structured way. So why we have chosen a particular database, like so product catalog, Postgres plus Redis. So it's a read heavy, complex filters, not products cached, and cart for Redis. So for orders, DynamoDB, high write throughput, partition by user. So like this for events, Kafka. So we need high performance central hub to process the events. So Kafka is good at processing millions of records per second, and S3 is good at storing the data, media files. Probably it can store a terabytes of data also. Documents, there is a good amount of upper limit for the media to serve from the cloud front end. Any stream for the streaming applications, most use S3 plus cloud front. Yeah, scaling challenges. So as I mentioned, for a system design, we need to think about for the fault tolerance and for the partial failure. So these challenges will face only a peak time like flash sale 10 times of the normal traffic in seconds. Our system should support. So we need to plan accordingly. We need to have our cache, and we need to have some load testing to be done in our internally before we experiment in production, so that we'll have more confidence. And sometimes inventory race conditions could happen if the many users using the at a time, purchasing that at a time, using the seeing the inventory by the two users, and two users basically buying the same item. We need to manage accordingly and efficiently so that user experience should be smooth. We should probably we should block the we should reduce that inventory. If the inventory is chosen by a first person, we need to have, and for other user, we should make sure there is out of stock. Instead, we are showing the false positive experience. So this is the critical, because what happens is these will come as a reviews for a product later on. I purchased a product on Amazon. There's a bad experience. It will impact the business. So business is also main focus on these things. With respect to this particular uh, platform, this is very important to provide the reliability for the application so that customers will trust it. And so these are another operation. Checkout experience should be very good. Having said this, 10 times of the normal traffic, we need to consider accordingly and have the a graceful message to the user. If it really there is happened, we should ask the user to wait for a moment and try again. So this is the common experience we see for a an application which is at high load. Search at scale is also. If the inventory grows, we need to scale accordingly. Uh, so the key takeaways on high level, like, so we need to start from the requirements and constraints. We should ask as many questions as possible and to get clarity on the requirements, functional requirements and non-functional. Functional requirements, mainly functional requirements and constraints. So that, and also non-functional also from the product. And if possible, we need to have some quantifiable numbers, how many transactions per second this particular API or service needs to support. Accordingly, we can design, and we need to define the right primitive, right trade-off for the cache. Anytime in the system design, we should have alternatives. That is the tricky thing, which one to choose. There is a cache, Redis is there, mem cache, which one to use. So we should avoid over engineering, and we should start with the simple. For example, if you are starting with a startup application, we could straight away go with the MySQL database and start building it. Later on, we can go with the typical databases like PostgreSQL. It is very advanced and it will support very high concurrency and all. So there are categories where the simple database, simple Spring Boot application layer, some kind of things are there to experiment and all. But later on, when we scale, we should have the proper uh, tools and services we need to use. And definitely, we need to think of design for failure, not only for happy parts. And failure of what happens if this system is down, this consumer is down. Having said this, as much as possible, we need to have design for failure. Sometimes there is a real failure, we cannot do anything, but we should have proper information for the developer, what happened actually. So we should have logs, those kind of things. So, and graceful message to the user. So this all comes in the design for failure. And the final and important thing is observe and iterate. So we need to observe and iterate our product, like how it is working, how it is operating, how it is serving, how many issues we are facing, how the customers are growing. So it's all about everything, and we need to iterate the product accordingly. So based on the feedback of the how it is serving for the customers. Yeah,
So, Venkatesh, there
thank
is a
you,
question in the chat. You
everyone.
might want to look at that.
Yeah, sure, sure. Okay. But how VMs can be used, how important as they in preparation of the system design, particularly when you speak about performance latency. Yeah, sure. Thank you, Sudhir. So, virtual machines is the okay. So different services provide these virtual machines. How we can use, like, are they in preparation of system design? So I will take an example like Amazon Web Services provide uh, virtual machines like EC2 instances. So as an example, it can be used like, so we need a real virtual machine to process. You need to do some customization and to have services deployed in a separate missions and scale accordingly. We could go with the VMs so that it will have its own operating system and like that. And there are some systems like okay. So this could be like one of the option. If you have a Kubernetes cluster, as an example I'm giving, so how we can efficiently use this one. If you use the Kubernetes cluster, we should need a nodes there. We could have EC2 nodes there as a separate virtual machines. They can independently scalable based on the template and the users. So coming to the attributes, how we solve this with this is as we put a load balancer behind this, as could be elastic load balancer if you could put it at, and we can scale in or scale out our EC2 instances. That is the one way to traffic the uh, one way to serve the high traffic using scale in and scale out our EC2 instances. with the elastic load balancer. That is the one way. Other way is if it is our Kubernetes cluster, as our nodes are itself VMs, we can use orchestrate, and we can have our replica set configuration is there in the Kubernetes. We can uh, scale in and scale out our VMs accordingly. So these are the every solution has its own trade-offs. Based on our application, we need to choose, and it will provide a proper experience for the user, because only a single server is not overwhelmed here. So the traffic is increased, traffic is distributed based on the algorithm, probably even if it is distributed eventually evenly, so that we will provide a proper response and we will get a low latency. Because for 100 users, if you are serving from one mission versus serving from 5 missions, so latency will be very low, and that way we can achieve it.
Hey Venkatesh,
There is,
such
yeah,
a good explanation. Yeah, I was totally spellbound. So I was listening to everything that you explained. Such a good experience listening to you. So I just want to share a couple of things. So first is like it was an eye opening, like the 99.999 or just 99, just that 1% or 0.11%, the difference that it makes, it's very eye opening. Like, so just 1%, when you stretch it over a period of 1 year, it's 3 days. That's crazy to even imagine. So that was such an eye opener. And next is like my specialization is Node.js, and in a previous company where I worked for 4 years, we are doing just Node.js and everything. So akkada, like we had a single virtual machine, and just a single one. And inside that, we Node.js has something called clustering. The single server, you can divide into, you can spin up multiple clusters, you can fork multiple clusters like 20 based on the cores of the CPU that the server is running on, right? So does that, is it a pure horizontal scaling, or we need separate VMs, separate multiple VMs? Is that horizontal scaling? How is it like that? Can you throw some light on that?
yeah, sure, Shashank. So could you please repeat the last sentence? I missed.
Yeah, so Node.js
You were stop.
has,
Yeah.
we are, yeah, the Node.js is hosted in a single virtual machine, single VM.
Okay.
And but
Hmm.
inside that, the single Node.js server can be spun up into multiple instances. So
Hmm.
so is that horizontal scale? Because it follows a round robin approach. The Node.js, that's the inbuilt algorithm that follows. So can we call this also, like, is it also pure horizontal scaling, or how? Like, I want to hear from you. Like, how
Yeah,
does it
sure, sure,
fit
Shashank.
in this context?
Sure, Shashank. So basically, when we say horizontal scaling, we should not take more VMs and all. So it comes with the cost to take a different VM and all. So it's challenging. Horizontal scaling, nothing but we need to have a separate instance running in a, say, for example, you can have a containerized applications. Like, so if you have a Docker container, it has its own isolated environment to run your application. So we need to increase the Docker containers having only one virtual machine. There is only one virtual machine, but logically Docker is very helpful. It will share the same kernel, but provide the different experience, different isolated environment to run our application, and we can easily enhance our applications. I mean, horizontal scaling, and uh, but using same operating system. So this way we can efficiently utilize the single operating system and serve horizontally instead of having a separate VMs. It's a trade-off. So when we really need it, we need to do that, but based on the application, but based on the traffic users, so we could have a good containerized application having a Kubernetes application to orchestrate these containerized applications should be sufficient on the single VM. What I would prefer.
Okay, cool. Yeah. So cool. And last thing, I'll take just 30, 40 seconds. So monolith versus microservices, right? So again, in our previous organization, I worked there for 4 years. The first 3 years, we were running a single monolithic server. We had each and every damn thing put there. The payment service, the communication APIs, the any inbuilt, middlewares, whatever it is, everything we put in one single VM. We have to, if we had to update one small thing, we have to redeploy the entire project, the entire server once again. So that's the exact point that I saw in your slides. So to solve this, in the last year, we split those components into separate small services which are independently deployable. We use serverless functions there, so because it was suiting for our use case. So is that correct? Is this approach correct? Is this what you're trying to? So we split a big monolithic project into small microservices, and each of those is independently deployable, and it doesn't have anything to do with each other with respect to the it's freely connected. It's not, it is loosely coupled. That's the right word. It's not tightly
Right.
coupled. So is this a good
Right.
example what we did in there?
Right. Right, Shashank. So any most of the business, because microservice architecture is today's trend, and from the couple of years, most of the applications in legacy, after if you take 8 years back, are all are started with the monolith starts framework, and it's a big application. It's a bloated application. When I was working with the JP Morgan also, there's a big banking application. Is a very sensitive application as an example. So, but it is not. Friendly for scaling. So it's hard to scale and it's very critical information. All the operations are very, very critical. So application is critical. We need to decompose. So different team needs to work on if the monolith, the language is scattered. I mean, so the single point of failure, right? So a big war file we need to deploy. There are several challenges and monitoring, scaling. So it is the right time for microservices. So the migration on a high level, I will tell how it will start is like it's not like that. Hey, this particular package deploying a service. It's not like that. So we need to work on the thing like we need to identify the boundaries of that particular service, what this particular payment service needs to do, and what data should go into that service. We need to decouple into a separate package and everything. Then we need to slowly deploy into the separate service. And initially, we need to use the two-phase approach. First, we need to rely on the monolith module, and slowly we'll get the process the request from the microservice. Once it is stable and data is migrated based on the flags, read flag, write flag. Slowly, we need to get the data from the microservice, and slowly we need to decommission the monolith. So it's a slow process because it is on everything is on live. We don't have time to I will build the microservice and deploy. It's not like that. So that is the one big challenge we say for an active application to migrate safely. That's a big challenge. So that is the reason we need to think about the microservices from the start. I mean, initially, on the startup, it is definitely grow and we are good to scale. At the moment, we need to put some effort and have a microservices and yeah, yeah, Richard, so the features of microservice independently work, independently deployable, and the technology choice we have and everything. Yeah, and it has its own challenges. When it is a microservice, you need to have proper inter-service communication, proper failover mechanism, and everything, monitoring and dependency. Yeah. Hope I answered your question, Shashank.
Yeah, absolutely. Yeah, such a good explanation. Yeah, I was totally spellbound throughout the entire presentation. Such a beautiful, session to have tonight, and looking forward to hear more and more sessions from you. I'm always up for it. Thank you so much, Venkatesh.
Yeah. Thank you, Shashi. Thanks a lot. Thank you, everyone, for your time. And yeah, hope it is helpful, everyone.
Yeah, thanks, Venkatesh. Good one.